I'm about to open up that channel right here, right now.
Oh, nice.
If I apply a small signal to the gate right now, and the channel opens up. Geekha! Hello everyone, Samsung Semiconductor Newsroom subscribers. I am Dragon, a maker from Geekble.
Dragon?
Yep.
You're looking great today.
Today, I've finally been given this long-awaited opportunity to truly delve into the topic of electronics, and that's precisely why I am here. At Geekble, everyone's always saying, no one understands electronics. Electronics are too hard, which often leads to me getting cut from the However, I'm going to demonstrate right here and now that what they say is absolutely not the case.
But what's with all this strange stuff you've got laid out on the desk today? What are these?
Come on, you've seen these before. They're switches. A switch, a valve, they open and close things.
Oh, is that red one a switch too?
The red one is a switch. Orange. Switch. Switch, valve.
But why did you bring these today?
The truth is, the very foundation of all the electrical magic we currently experience and benefit from is rooted in this tiny switch right here. Anyway, Gokwi, do you happen to know what the smallest of these switches is?
The smallest switch?
Can't you spot the smallest one? It's here with me.
There's something smaller than these?
Can't you see it? Right here, you don't see it? This thing is called a transistor. And yes, it's a switch too. It opens and closes depending on whether electricity is applied. This is also a switch.
Oh, geeks always explain things like this. When you talk that way, I can't understand it. Actually, today, the Samsung Semiconductor Newsroom entrusted us with a mission. The mission we were given was, can you make it easy for people to see how tiny switches can change the world?
Oh.
But when you look at a semiconductor chip, it's only about the size of a fingernail, and you can't even see the circuits inside.
Yep.
Can we actually make one big enough to see?
Of course we can. Electricity itself is invisible, right? That's why people find it so hard to understand. But once you think of it like water, it all starts to make sense.
You mean you can explain electricity with water?
Yeah.
Now I'm really curious. So, are we making a semiconductor that works with water instead of electricity?
That's right, it's semiconductor, water semiconductor.
Perfect. We actually prepared something else too.
Oh no, what now?
You know the special suits that engineers at Samsung Semiconductor plants wear when making chips? Since we're making a semiconductor too, shouldn't we wear clean room suits as well?
Do we even have those?
Why, yeah.
No!
This is an actual clean room suit worn by Samsung engineers. You can't even buy these anywhere.
Wow, are we really doing this? I'll go put it on right away. Wow, I'm back. This is what real engineers wear, right? And one thing I'd always been really curious about was exactly how this protects the semiconductors. But just take a look at this. You can't even feel air passing through.
I saw somewhere that when engineers work, they're completely sealed up so not even a single speck of dust can get in.
Then, can we finally start making?
Looks like you're ready. Why don't we experience how a transistor works first and then start making?
You still don't get it, huh? So, how would you turn on this light bulb?
You flip the switch, right?
Exactly. Like this. And to turn it off? Like this.
That's just a normal switch we all know.
Right. Currently, a person's hand physically manipulates this. However, by regulating it with the presence or absence of electricity, or the ebb and flow of electric current, you can toggle it on and off countless trillions of times each second.
One more thing, I still don't get it. So what exactly does a transistor look like and how does it work? Can you show me?
Show you? I'll make one. We're going into the world of nanometers now.
Wow, the world of nanometers, I love it. Shall we, Joe?
Let's go!
Dragon, how's the design coming along?
First of all, I'm going to build it like this.
What? This is a transistor?
Well, basically, in an electrical circuit, the water inherently wants to flow and seeks to move freely like this. The black part means it's closed and the white part means it's open. In this model, water represents the flow of electricity.
Got it.
Water equals electricity. Now look at the syringe below. Like this. If I push it like this, what fills the inside?
Air, right?
No, water. So when electricity fills it up.
Oh!
And when the electricity drains.
The principle is pretty simple.
It is simple when you see it like this. But imagine making this on a nanometer scale. That's where it gets tough. We tried positioning this syringe upright in various ways, like this and that, and even enclosing it. Just consider the immense blood, sweat, and tears countless researchers poured into making this device so incredibly minuscule.
So does that mean we're done now?
Not yet. The design isn't finished. I've tried my best to design this based on my understanding, but I'm truly unsure if this precisely aligns with the operational principles of a transistor.
In that case, how about we directly consult with an engineer who is currently working in the field and actively involved in the production of semiconductors?
We can do that.
Sure, how about we call him right now?
Cool, let's do it.
I'm dialing now.
停顿，停顿。
I'm making the call now. No batting out.
Yes, hello?
Hello, sir. I'm Sue Dragon, a maker from Geekble, where we share the fun side of science and engineering. Nice to talk to you.
Hi, nice to talk to you. I'm Lee Junhan, a semiconductor engineer at Samsung Electronics.
It has always been a heartfelt wish of mine to meet and converse with engineers like you. It is truly an immense honor to finally have this opportunity and meet you in person like this.
No, the pleasure's mine. It's great to talk with the Geekble team.
Well, the main reason I'm calling you is because I was racking my brain trying to figure out how to easily explain transistors to people. And then the water channel analogy popped into my head. The particular structure of the valve I'm currently designing works by opening and closing in proportion to the amount of water that fills a syringe, allowing for a really clear demonstration of the concept.
Okay.
So I was wondering that this design is closer to an FET or a BJT.
Well, since FETs are voltage-driven devices, I'd say your syringe analogy, where pressure or water level acts like voltage, fits an FET.
Ah, the syringe height represents voltage, so when it changes, the valve opens or closes. That means my model basically mimics an FET structure, right?
Yes, that's correct.
So my understanding and design are roughly correct. I'm so happy to hear that. With your advice, I'll do my best to make something that helps anyone understand how a transistor works.
That's great to hear. I really enjoyed our talk.
Oh, thank you so much.
Thank you.
Wow! Sue Dragon, I'm so impressed.
Feels like I can finally cross one thing off my bucket list. And I'm glad to know my design wasn't too far off after all.
Perfect. Then let's finish the design based on what we learned.
Yes, still a long way to go. Let's do it.
Sue Dragon,
Yep.
the moment has come. So first, can you walk us through how this circuit is set up and how it works?
Yes, so we have a voltage source right here. The power supply, originating from the voltage source, is currently connected to the drain terminal of the transistor. And depending on the gate state, electric current will either flow to the source or be interrupted, effectively switching it on or off. And what exactly controls that? You are now going to witness how this expansive water channel will either open or close, all by means of just a tiny signal applied at the gate. Alright, first things first, I'm going to open up the valve and then I'll proceed to connect it directly to the drain right over here.
Power is coming from the battery now.
It's filling up, right?
Oh, yep.
The electricity is coming in.
Yes, looks like there's a little leakage, but it's not affecting the main flow yet.
We're leaking a lot toward the gate, but the important thing is that nothing's flowing to the source yet.
Grounding's not great.
Alright, it's completely filled up. Now I'll open the path between the drain and source.
Let's go! Oh wow, the current's really flowing now, right?
Exactly. See how the water is rushing to the source? The key is controlling a big valve with a tiny force. So with this small gate signal, we can close it and open it. That's how we create the 1, 0, 1, 0 of electricity.
Seeing it like this makes it way more intuitive. But I think this prototype needs an improvement. Not perfect yet.
I admit it, you've seen on our flow. But how does this really act like a switch? With just this dripping setup, what can it actually do? You might be wondering that right now. So next, we'll show the real switching in action, turning the flow on and off to control something like an LED or a light bulb.
Exactly. We have to show that too. You'd feel like something's missing otherwise, right?
Yeah, exactly. Ah, what's wrong with the gate?
Alright, let's improve it.
Let's do it.
Let's go, let's go. Sue Dragon, don't you ever give up now.
This isn't the end.
Sue Dragon,
Yep.
we've personally conducted experiments to understand the transistor's principle, haven't we?
Yeah.
So now you're building a device to demonstrate how that very principle is applied in our everyday lives, correct?
Indeed, you could certainly say that.
Why did you think of this water wheel?
If electric current is flowing, when the current flows through this water wheel, will begin to spin. That indicates the electrical equipment can function, and anticipating that this might appear somewhat inadequate on its own, I've appended additional circuits to it to bolster its capabilities.
There's a lot attached back there.
See this gear linked to the water wheel. This specific gear, which is synchronized with the water wheel, identifies when the water wheel is in motion. Upon detecting this movement, the microcomputer then processes these received signals, subsequently transmitting them to a designated switch, commonly known as a relay, for further action, and activates another switch, a relay, to turn a light bulb on or off. So today, we'll learn how a transistor controls the flow of electricity in any device.
Wow. Are we ready to start the experiment?
We are.
Yay!
Let's go!
Woohoo!
All set! Preparations are finished. Now, some things have changed since the day before yesterday. To begin, we've got the voltage source and the transistor, just as before. This aspect remains unchanged, but the real divergence lies in what we're about to do. We're going to manipulate the water wheel right here, turning it on and off, making it rotate, and then bringing it to a halt. And to make it even clearer and more visible, I have also connected a light bulb to it so that we can clearly see the effects of the experiment. Therefore, today we'll be able to see not only the core principles of transistors, but also their practical applications.
Oh, excellent! So, we'll gain an indirect understanding of how semiconductors are truly transforming our everyday lives.
Right.
But if you remember, we did encounter a rather significant problem when we conducted our last experiment, didn't we?
Yeah, there was some leakage. So, our solution? We will now apply water-resistant grease. Once the grease has been applied, we'll start the experiment with the gate held in a closed position.
Oh, looks like there's no more leaking current from the transistor.
It's much reduced, right?
Yeah.
Alright, at this very moment, the gate is obstructing the pathway connecting the drain and the source. Alright, from this point forward, if I allow the passageway between the drain and the source to open up, the channel opens. The water wheel spins.
No!
And the light turns on. When we close it again, the water wheel stops and the light goes off.
Can I try?
Sure, come on in.
So this is the transistor, right?
That's right.
If I send a signal from the computer. Oh!
The channel from the drain to the source opens and flow starts.
And if I shut it off this way, in reverse?
We sent an off signal. This small signal caused the channel from the drain to the source to be cut off. Consequently, when the electric current is interrupted, all of the connected devices cease to operate.
Our mission, success. Oh. High five, high five.
High five, we did it. I thought it wouldn't work.
Wow, Sue Dragon.
Yes.
We successfully wrapped up the experiment today.
Looks like luck was on our side today. That was tougher than I expected, but this was something I've always wanted to try, and getting to do it here on the Samsung Semiconductor Newsroom makes it even more special. To be honest, I'd say this mission from Samsung Semiconductor Newsroom is. I'm going to predict that this is a complete success. This has been Geekble and Samsung Semiconductor Newsroom. Geek bye!